So let's look at this mock exam, question number 1. And of course, the directions are important. You do have 25 minutes on this part of the exam, and so this is critical. You don't want to spend 5 minutes on it, and you can't waste a lot of extra time on it. This is 55% of your score. Read this on the AP test so you'll know how long they sort of think that you're going to spend. And it says, of course, explain your methods. It's a free response question, so it's not only the accuracy of the answer, but it's the completeness of the explanation that gives you the credit. Read the question. I'll admit this one took me a couple of times to read it to make sure that I understood exactly what was going on. We've got some students turning in work. Some of them turn it in complete. Some of them turn it in on time. Some of them miss both of those marks. And it says assume the assignment submissions are independent of each other. Given that an assignment is late, what's the probability that it was completed? Now, it doesn't explicitly say this in the rubric for this question, but I think it's a good idea to say things like C means the assignment was complete, and L means the assignment was late. I think that's a good idea to include stuff like that in your answer. And so as I look back through here, I see that 85% of the students turned it in complete. 85% of them turned it in complete. 80% turned it in on time and complete, and 93% turned it in on time. So if 93% turned it in on time, then the probability it's late is 7%. And what I've got with this formula is going to tell me that this is the probability. It's a fraction here. On the bottom is the probability it's late, and on the top it's the probability it's complete and it's late. Now we just said the probability it's late is 0.07. The probability it's complete and late can be found by looking at these two numbers here. 85% chance it was complete, 80% chance it was complete and on time, which means there's 5% that were complete and late. That gives me an answer of 5/7. You could leave it as a fraction, or if you want to put it as a decimal, that's approximately 71% of the time. I think having your answers written in context is a great habit, and maybe even a habit that will earn you points on the AP test. And so I would say something like this. The probability that a random assignment was complete, given that it was late, is about 71%. I'm not a good typer, so I misspell a lot when I type. Spelling is probably not going to be point worthy on the AP test. So that's how you do the first question. Now the second one says, if he randomly selects assignments one at a time, what's the probability the first one he finds that is not turned in on time with every question complete is one of the first 5 selected? So when I see this first 5 selected, I think about a geometric distribution. Now, geometric distribution says we're going to go until we succeed. Each observation is a success or a failure, and the probability is constant each time. Finally, the assignments are independent. It told me the assignments were independent, and I know that in this case, there is an 80% chance that they're on time and complete, so there is a 20% chance they're not on time and complete. And so what I end up with here is a geometric situation. I think defining these again is a good idea. I would do that. Now again, that 20% came from right here. It's 1 minus 80% are on time with them complete, so 20% are not that. And what I'm looking for here is the probability that that first one is one of the first 5. And so if I'm showing work here, that means it could be the first one, or maybe the first one was not that way and it's the second one, or maybe the first 2 were not that way and it's the third one, or maybe the first 3, say a parentheses and a 3 like that, the first 3 were not that way and it was the fourth one, or the first 4 were not that way. Now I can expedite this mathematically by doing this calculation in my TI. It's the GeoMet CDF because it's a cumulative one where there's the probability of success and I want to know it occurs here, and this is going to be 0.67232. Again, stating that in a sentence form is a great idea. There's about a 67% chance that what they asked will happen. Some students may choose to use this as a binomial distribution, and binomial, you would say, what's the probability that if I do it 5 times, if I want to use binomial, I'm going to try 5 times with a 20% chance of success, and I want there to be 1 or more successes in that group of 5. That's a perfectly acceptable way to do it. So here we want to describe the distribution for these 70 students of papers that are turned in complete and on time. So papers that are complete and on time, when I go back here, that's this 80%. And so I want to know if I have 70 students and the probability it's complete and on time is 80%, what does that distribution of the sample proportion look like? Well, first we want to talk about the mean. The mean is going to be NP, or 70 times 0.8. Nope, not NP. That's not correct. Forget I said that. The mean, because of the central limit theorem, is going to be 0.8. This is the mean of a proportion problem. The center of this distribution is going to be 0.8. Now, I drew it as a normal curve. Is it normal? Well, it's normal if NP is greater than 10 and N1 minus P is greater than 10. So NP is 70 times 0.8. This is 56. That's definitely bigger than 10, so that's good. And N1 minus P, that's 70 times 1 minus 0.8, which is 70 times 0.2, which is 14. That's bigger than 10. Since both of those are bigger than 10, since both are greater than 10, the shape is approximately normal. And then finally, I need to talk about the spread. The standard deviation of the p-hats is going to be the square root of p times 1 minus p over n, which is the square root of 0.8 times 0.2 over 70, which is 0.0478. And I can say all this succinctly. I'll type it by saying this. Sampling distribution of the proportion of papers that are turned in on time and complete in a class of 70 students is approximately normal, with mean 0.8 and a standard deviation of 0.0478. So this problem asks how you would conduct a simulation. Notice it doesn't say here to conduct one. It just says how would you conduct a simulation to estimate the probability that at least 68 of the 70 students turn in an assignment on time. All it says here is on time. Back at the beginning, it told me that 93% turn it in on time. So what's the probability that at least 68 of them do? We're going to use a simulation here. So let me explain what I'm going to do, and then I'll write it up for you. The probability that a student does it on time is 93%. So what I want to do is assign the numbers 01 to 93 to represent an assignment that's on time, and 94 to 00 is ones that are late. I'm going to look at 70 consecutive numbers, pairs of numbers representing the 70 students, and count how many of those numbers represent papers that were on time. In other words, how many of those pairs of numbers are between 01 and 93. If almost all of them are, then that's a success in this trial. If there's more that are not, if I don't have at least 68 in there, then that was a failure in this trial. I'll repeat the trial a bunch of times and then see what proportion of the time I get at least 68 of the students turning it in on time. That will estimate the probability. So here's what I wrote up. There's a 93% chance they're on time, and using random digits 00 to 99, assign the digits 01 to 93 to indicate an assignment was turned in on time, and 94 to 00 to represent the late assignment. Select 70 pairs of numbers from the chart and see if more than 2 of them are between 94 and 00. If they're not, then this result was a success. Otherwise, it was a failure. Repeat the process a lot of times and record the proportion of successes that are observed. This proportion is the estimate of the probability. So here the explanatory variable is the method of learning, whether it's traditional learning or remote learning, and the response is whether or not the assignment was completed on time. I'll type that for you. So there you go. Now, is this an observational study or an experiment as we head into the next question? Well, the key question is, was a treatment imposed? We did not impose a treatment. We did not have a control group. We simply recorded results from before and after remote learning occurred. So we didn't manipulate the treatments. So no, therefore, this is an observational study. Otherwise, we would have needed to divide the kids into groups. Some of them get the remote learning, some get the traditional learning. Describe a method by which Mr. Atkins could use a matched pairs design to improve his study. Now again, this doesn't say to make it into an experiment. It says to improve his study. So if you go back here, you notice he found 50 random students before when they used regular learning, and then 50 random students when he used remote learning. One way to do matched pairs is to randomly pick 50 students, examine those 50 students in a before and after scenario. Now each student is paired with themselves. That's the matched pair. That will reduce the variability that may occur by picking random students. So that matched pairs design is an improvement. So now he wants to construct a 95% confidence interval for the difference in the proportion of assignments completed and on time for the traditional school group and the remote learning group. Confirm that all the appropriate conditions have been satisfied. All right, so what conditions do we need to have? Well, we need to have random samples, we need to have independence, and we need to have normality. So random, independence, and normality. Now, it's not okay just to write that and move on. This is just to help me keep it straight. Now, what is it that I'm sampling? I'm sampling assignments here. The way he's described it in Part H is he's sampling assignments. And so we need the random assignments. If we're going to do a 95% interval, we need to do random assignments from before and after the learning switch. Random assignments. For independence, this is where we need the 10% rule. So he's going to sample 50 assignments. I think it's, yes, 50 student assignments. Now, I did do a great job of differentiating between the students and the assignments before, and I probably should have, because he's randomly selecting assignments here, so there should be more than 50 times 10, or 500 assignments before and after the learning change. Now you may say, hey, that seems like a lot, but it's total assignments. So within the classes, he can probably get to 500 pretty quickly. And so now we've got to the normality, and we need to have at least, can't spell today, at least 10 successes and failures in each group. So let's check it out. Well, in the traditional group, we had 37 successes and 13 failures. And in the remote learning group, we had 30 successes and 20 failures. Since all of those are bigger than 10, we've got approximate normality. And that would allow me to confirm the conditions have been satisfied. And so now it says here they did the interval, they got this, interpret the results. Based on this confidence interval, do you believe there is convincing evidence that the proportion has decreased? Okay, so this is a negative percent and this is a positive percent. And so what we find is that there's somewhere between, the completion rate is somewhere between a 4.23% less and 32.23% more when they did the traditional learning. So the traditional learning seems to have a higher rate, but it might actually be a lower rate. That's what this negative means. 0 is in the interval, so I do not have convincing evidence that the proportion has decreased. If I was doing a hypothesis test, my p-value would not be significant. So let me write that up for you. So there's a good way to write all that up. In a different video, I'll go through grading for this.